Welcome to today's lecture. It's entitled Estimating Population Values. Okay, so this is the topic after distributions. So at the end of this discussion, we should be able to distinguish between point estimate and a confidence interval. We should be able to construct and interpret confidence intervals for means, proportions, and variances. Okay, so there are different cases for constructing a confidence interval for the mean, the population, proportion, and also the variance. And we need to be able to know what formulas to use in each particular case that is presented to us. Okay, an estimator of a population parameter is just a random variable that depends on sample information. So the value of that random variable that you're using to estimate, the value of the random variable is what we call an estimate. Okay. A point estimate is a single number, while a confidence interval provides a range of values for the population parameter which we are estimating. So as you can see, we have the point estimate there as the value, and the confidence interval is that range. Now, we have seen point estimates in the previous discussion on the previous topic. We used the sample mean to estimate the population mean. So our sample mean was our estimator. And we also used the sample proportion to estimate the population proportion. So that means our sample proportion was an estimator. Now, sometimes we want to know whether that estimator is biased or unbiased. So an unbiased estimator is just an estimator whose expected value or mean is equal to that of the parameter. Okay, so we're saying the expected value should be equal to the parameter. The sample mean, we found in the last topic that the expected value or the mean of the sample mean is just the same as the population mean, which makes the sample mean an unbiased estimator of the population mean. We also found that the mean for the sample variances was the population variance. Okay, so that means that the sample variance is an unbiased estimator for the population variance. And we also did find similar, we also found that the sample proportion is an unbiased estimator of the population proportion. Okay, so we need to know if an estimator is unbiased, then it will be centered on the parameter. Okay, but for an unbiased estimator, theta 2, we see that it is centered there. Its mean is not that the mean of the population parameter, therefore it is not biased. But theta 1 has a mean, okay, or the expected value is the parameter itself. So that means that theta 1 is an unbiased estimator. For us to see the biasness of an operator, for us to see the biasness of an estimator, we can subtract the parameter from the expected value of that operator. And we can see that actually for an unbiased estimator, this difference will just be 0 because they are the same. Okay, so apart from an estimator being unbiased, we would want to know if our estimator is also the most efficient estimator. And the most efficient estimator is just the estimator with a minimum variance. Okay, so in this case, if theta 1 has a variance, if this was the variance of theta 1 and variance of theta 2 is greater than the variance of theta 1, then we say that theta 1 is the most efficient estimator. Okay, and the relative efficiency of theta 1 with respect to theta 2 is just found by using this formula. Okay, so we have seen that we can use point estimates, but sometimes it is good to use a confidence interval because you are able to come up with a range of values. So you can therefore make your estimation based on that range of values that you've obtained. Okay, so an interval estimate provides more information about the population characteristic than a point estimate. And then we have seen that those intervals are what we call confidence intervals. Okay, so confidence intervals are based on observation from one sample, and they give information about closeness of an unknown parameter or population parameters. Okay, then we can also never be 100% confident. Okay, so the confidence level is known as 1 minus 100. Okay, I mean the confidence level is given by 100 multiplied by 1 minus alpha percent. Okay, so take note of our alpha here. Okay, so 1 minus alpha is the confidence level, and it is between 0, and alpha is between 0 and 1. Okay, so what we are just saying here is that we can find a sample from a population, estimate the mean, and then create a confidence interval, which gives us an idea like the the mean is supposed to be between 40 and 60. Okay. Now suppose our confidence level is 95%. Then we're saying that 1 minus alpha is equal to 0.95. Okay, so that means our alpha will be 0.05. So we'll have specific interval, we'll have a specific interval will either contain, no, a specific interval either will contain or will not contain the true parameter. Okay, but okay. Now, the general formula of a confidence interval is just given by the point estimate plus or minus reliability factor multiplied by the standard error. Remember from the previous topic that the standard error is just the standard deviation of the sampling distribution. Okay. So the value of the reliability factor depends on the desired level of confidence, and we'll see how this is drawn. So we can construct confidence intervals for population mean, population proportion, and population variance. Okay, and for us to construct the confidence interval for population mean, we have two cases. The first case that we'll consider is if the standard deviation is known. If the standard deviation is known and the population is normally distributed, then our confidence interval will be given by this formula. Z alpha over 2 is also known as our critical value. It's the Z value for a particular alpha. Okay. Now we can generalize the formula that we've been given. We have we're just saying we have the point estimate. The point estimate. We can generalize the formula of a confidence interval, which can be written as the point estimate plus or minus margin of error. And margin of error is also known as sampling error. Okay, so margin of error is just the reliability factor multiplied by the standard error. So the margin of error can be reduced if the population standard deviation is reduced, the sample size is increased, and confidence level is reduced. Okay, so how do we get our Z values? We have already dealt with the normal distribution. So here we are told that the area inside should be 0.95, which is our for 95% confidence level. So that means we subtract this from 1, this 0.95 from 1. We're going to see that the area that remains is 0.025. But we have two sides, okay? So if we have two sides, then we're going to divide this alpha 0.05 by 2, and we have a 0.025. So this is the area this side, and it is also the area on the other side. But we're interested in this value that demarcates the area we're interested in and the area that remains. And this we can find from our table. Remember, from our table, we're finding the probability when we've been given the Z value. But in this case, we're looking for the Z value when we have the probability. So you can go on your tables, look for the probability that gives you 0.027, okay? And look at this, your table reads the values on the left. So if you're looking for this probability on the right, it is 1 minus this 0.25, which is a 0.975. So that probability, go on the probabilities, the probability should be 0.975, and then look for the value, the Z value. The Z value that you're going to find will be 1.96. And the other side, you're going to find a minus 1.96. So this is your value, Z value, but it is also known as the critical value. So some Z values have been provided for you. At 80%, we get that. So you try to find this on the normal table. You are able to do this. Okay. So we say that actually the confidence interval contains the mean. So a study or an experiment that was done was actually found that for different sample sizes with a fixed mu and a fixed n, okay, then it was found that almost all the intervals created contains the mean, but only one did not contain the mean. So here we can conclude that when you make confidence intervals, 100 multiplied by 1 minus alpha will contain the mean, and only that other percentage will not contain the mean. Okay, let's have an example. A sample of 11 circuits from a large normal population has a mean resistance of 2.2 ohms. We know from past testing that the population standard deviation is 0.35 ohms. Determine a 95% confidence interval for the true mean resistance of the population parameter. Okay, so we put down our data, we have a 95%. Okay, so then we also put across our formula. So our formula says we have to take the mean. So the mean there is 2.20 plus or minus the Z alpha over 2. The critical value for Z at 95% confidence level is 1.96. Okay, so then we multiply with the 0.35, which is the standard deviation over 11, and this is our sample size. Okay, so what we see there is that we get a confidence interval that is between 1.99 and 1.9932 and 2.408. 2.4068. So this just means that we are 95% confident that the true mean resistance is between 1.9932 and 2.4068. Okay, so we now look at the cases. The next case when the standard deviation is unknown.